Hello and welcome back to Physics Online, where today we're going to be discussing graphical analysis. We're going to be taking a look at some graphs and analyzing them and coming up with some conclusions. But first, let's do a little bit of review. I want to define average velocity and average speed. There's two different definitions. Even though these two terms sound like they should be the same, they are not. So I want you to work through this problem right here, which we looked at in an earlier video. Find the total displacement and the total distance. And then, if it took 10 seconds to complete the trip, calculate the average speed and the average velocity. So hit that pause button, and then we'll come back and compare our answers. Okay, let's compare some answers. First of all, for the resulting displacement, we go 4 meters north and then 4 meters east, connecting tail to head, 4 meters south and 4 meters west. And as you can see, there's nothing left over, so the total displacement for this trip was 0. On the other hand, the total distance, where we ignore direction, will be 4 plus 4 plus 4 plus 4 gives me 16 meters. Now, to calculate the average speed, to do that, average speed is a scalar quantity, and so it should be expressed in terms of a scalar quantity. Distance is a scalar quantity over the total time, so we can write this as x being our distance and t for time. In this case, the total distance traveled around this trip here was 16 meters, and it took 10 seconds, according to our information here. So our average speed was 1.6 meters per second. On the other hand, average velocity is a very different quantity. To find average velocity, it will be the total displacement over the total time, and that can be expressed in terms of my change in position, delta x, over the time period, delta t. And as we mentioned earlier, the total displacement was 0. That's what we got up here. And dividing that by 10, we get 0. Okay, now notice that we use v to designate average speed and also average velocity. We can't use s for speed because s stands for second. So the only way we're going to distinguish speed and velocity is when we talk about speed in relationship to total distance traveled and average velocity in terms of total displacement. Okay, now I want to move on and take a look at another aspect of this type of problem, and we're going to take a look at graphical analysis. Suppose a girl travels at a velocity of 1 meter per second for 30 seconds. She then stops to rest for 10 seconds and then returns to her starting point at a velocity of negative 1 meters per second for 30 seconds. And negative meaning the direction. She's now moving in the opposite direction. What I would like you to do is calculate the displacement during that first 30 seconds when she was traveling at this velocity, and calculate displacement during the next 10 seconds, and then finally calculate the displacement during the last 30 seconds. Use this information and use the fact that velocity is equal to the distance or displacement over t, and use the equation for displacement from this equation right here. So push that pause button and let's see what you can come up with. Okay, here are the answers I came up with. Again, we can use the equation for velocity or speed, simply solve for x, so we have x equals velocity times time, so that's what I have here. Substituting in for 1 meter per second for the velocity and for time of 30 seconds. During that first 30 seconds, the displacement is 30 meters. During the next 10 seconds, however, she's at rest, and so the displacement would simply be 0. There is none at all. And in the last 30 seconds, now she was traveling in the opposite direction, negative 1 meter per second, times 30 seconds gives me 30 meters. And note that basically we can see that the units are correct because over here we have seconds, cancels with seconds, and I end up with meters for my displacement. And the same thing here. This seconds cancel with this seconds, and I end up with meters. Now, what I would like you to do is take this information here and draw a position versus time graph for the entire trip and label your axes. In other words, along the vertical axis, you're going to have x, that is the particular position, and then along the horizontal axis, you're going to be plotting the time in seconds. So push that pause button and see if you can sketch this position versus time graph. Well, this is the position versus time graph that you should have gotten. In the first 30 seconds, the displacement was 30 meters. In the next 10 seconds, she was at rest. And then in the final 30 seconds, she reversed her direction and the displacement was negative 30 meters. So basically, she came back to her original starting point right here on this axis. Now what I would like you to do is calculate the slope for each part of this trip. During the first 30 seconds, that is this part right in here, and we could label that A. And then in the next 10 seconds, that's this part of the trip right in here, B. And finally, the last 30 seconds, this part right in here. I want you to use the slope formula, remember it's rise or run, and calculate the slope for each of those various parts of this trip. So push that pause button and let's come back and compare answers. Okay, here's our results. The slope is the rise of the run, which is my change in position over the time period. And I chose 2 points, one of them being the origin right here and the other point right here. So we get 30, that's this distance minus 0, and then the time is 30 seconds minus 0, and so I get 1 meter per second for this part of the trip right here. Then this slope, which again is the change in position delta x over the time period. During the next 10 seconds, it was 30 meters here, but then she stayed at rest, so she's still at 30 meters from her starting point. So 30 minus 30 gives me a 0 over that 10 seconds, and so her velocity was indeed 0 meters per second. Finally, for the last part of the trip, I use this point and this point. Her final position was 0. She was back at her starting point. Initially, she was at 30 meters, so it's 0 minus 30. The time period was 70 minus 40, which gives me a negative 30 over 30, which is a negative 1 meter per second. So we can see that basically these are the velocity values that were originally given in the problem. So what we conclude here is that the slope of a position versus time graph will give us the, well, what goes in this blank? It gives us the velocity. And we can express this slope as I said before, the change in position over the time period, and that does indeed give me the velocity where delta x is the change in position. Now, calculate the average velocity during the first 40 seconds of this trip. In other words, what would be the velocity, the average velocity, during this first 40 seconds? So use my equation, delta x over delta t, and let's see what kind of an answer we come up with. Push that pause button and do some calculation. Here's my answer. The average velocity comes out to be delta x, which in this case is 30 meters. The time, however, now has been extended for 40 seconds, and therefore we get an average velocity of 0.75 meters per second. Notice it is indeed less than the 1 meter per second that we found up here, but that makes sense because now there was a period of time in which the lady was at rest, and so the velocity, average velocity was less. Now, I want you to examine the graph and find the instantaneous velocity at t equals 10 seconds, 15 seconds, and at 26 seconds. Now, by instantaneous velocity, we mean velocity at a particular instant in time. For example, if you're in your automobile and you look at your speedometer and it reads 30 miles per hour, that is your instantaneous velocity. Of course, it doesn't stay that way for a very long period of time. If you see a traffic light, then you're going to either slow up or speed up, and then the instantaneous velocity would change. So what I want you to do is take a look at this graph up here and figure out what the velocity is for 15 seconds, and what was the other times I gave? 10, 15, and 26 seconds. What is the instantaneous velocities for those particular values? So push that pause button and write down your answer. Okay, the values I came up with for the instantaneous velocity was indeed nothing more than the slope of 1 meter per second. In other words, if we take a look at our graph, we can see that the slope for this entire portion is equal to 1 meter per second, and that's the velocity. So at t equals like 10 seconds, that would be the velocity. At t equals 20 seconds, at 25 seconds, 26 seconds. In other words, whenever the slope right here is constant, then that value of the average velocity is equal to the instantaneous velocity. Now here it changed. What is the instantaneous velocity at 35 seconds? Well, it's equal to 0. What is it at 37 seconds? Well, the instantaneous velocity is still 0. That is, during this entire 10-second time interval, the velocity was 0, the slope was 0, and so the instantaneous velocity is going to be 0 throughout that entire range. Likewise, in this region right in here, the velocity at each point in time is a constant negative 1 meter per second. So we conclude, therefore, that whenever the slope is constant, then the average velocity is the same as the instantaneous velocity for that particular time interval. Now, let's move on and take a look at another graph. This time I would like you to sketch the velocity, use the velocity values above, and sketch a graph of velocity versus time. That is, you're going to have velocity along the vertical axis in meters per second, and along the horizontal axis you're going to have time, and I want you to use these velocity values that we found for our particular curve, that is this one and this one and this one, and sketch a graph of velocity versus time. So push that pause button and then we'll come back and compare answers.